we have section 7.1, dealing with differential equations and Euler's method. And before we start doing any problems, let's understand what a differential equation is. Well, first off, in the math sequence, college math sequence, we have Calc 1, Calc 2, Calc 3, and then differential equations. And so our first look at differential equations comes now. And very simply, the definition of a differential equation is an equation involving a derivative. Maybe not. And we define our differential equations by order. So if the differential equation has a first derivative, then it is a first order differential equation. Okay, and I have an example of one right here. dy dx equals x plus 1. So now we are going to be solving differential equations. So I want you to make note. If you see the word solve the differential equation, so if you are asked to solve the differential equation, or you are asked to solve dy dx, then what we are looking for is y. Y of x. And what is the operation that we have to do to get there? Sorry, I'm writing away. We need to integrate. We need to take an antiderivative. So this means that we are going to have to integrate to get there. Okay? All right, now, when we deal with these differential equations, there's something called a slope field that is very helpful in visualizing what the graph of the solution to the differential equation will look like. And so what I want to do is create a slope field. So let's do, change it a little bit. Let's do a grid that looks like this. And what I want you to do is put 3 points to the left of 3 points to the left of 0, 3 points to the right of 0, and let's make a square grid around that. Okay? And actually, we won't make a complete square. We'll just do a few rows because it'll take a little less time. So I want this grid of dots representing points on the xy plane. And we'll do one more. Yeah, that'll do. So we're going from -1, 0, 1, 2 up to 2. And we have -3 to 3 on the x. So that's our grid. And to create a slope field, we use our differential equation, dy dx equals x plus 1. Ooh, that's a 1. And what's another word for derivative in this class? Slope. The slope of the tangent line. So this differential equation, dy dx, is giving us the slope of the solution to this differential equation. So what we will do is we'll create a little table, and we are going to find the slope at each point in my grid. And to designate that slope, we will just put a little tick mark that has that slope on the grid. So if we look at it like this, let's look at 0, 0. 0 in the x, 0 in the y, dy dx equals x plus 1. So you plug in the x and the y. In this case, there is no y in my definition of my differential equation. So we'll do 0 plus 1. So what is my slope? It is 1. So then you come over to your grid, and at 0, you put a little tick mark with a slope of 1. Now, Does it have to be exactly 1? You'll do your best. What I do want to see is if you have some that have a slope of 1, I need to see that a slope of 2 is steeper, a slope of 3 is steeper still, and a slope of 1/2 would be less steep. All right, so in this one, what about all the points that have 0 for the x? What will their slope be? They'll all be 1. So 0, 1, 0, 2, and 0, -1 would all have a slope of 1 as well. Because in each of these, we're just doing x plus 1 to get the slope. So the whole row has the same. I'm doing the best I can on this Moby board to get the same slope, so it should be the same. All right, so take a few minutes and finish this grid. So let's plug in the next one. Let's do 1, 0. To get dy dx, we do x plus 1, so 1 plus 1 is? So when x equals 1, because there is no y in here, they'll all have a slope of 2. So I'm going to try and make those a little bit steeper. If I can. Like that. And then we continue. Fill in the grid. So our differential equation was x plus 1. If we took the antiderivative, we'd have x squared over 2 plus x plus c. So it makes sense that we get kind of a parabola shape. Now, if you don't see it, let me give you a few points. So what you're looking at is the general solution. So you're looking at a whole bunch of possible solutions. And let's say I said that the solution has to go through the point -1, 0. So if it goes through the point -1, 0, and you had to sketch a possible solution, you are not connecting dots, but you're following the slope. Nathan, hang with me here. Take that head up. Come on. All right. So we follow the slope. The slope is 0 here, but if I move to the right, you can start to see the grade go up. So it's going to look like this, best as I can. And then as I move to the left, which is not a strength for me on this board, we're looking at that. So there's one of our solutions. That would be a particular solution through the point -1, 0. All right, well, let's say it had to go through the point 1, 0.
So it's like when it gets to the point x equals 0, slope of the parabola at that point is 1?
At x equals 0?
Yeah.
Yes, exactly. So when it gets to that point, it will have a slope of 1.
Okay.
Yes. The solution will have a slope of 1. All right, so let's say it has to go through the point 1, 0. So that means this point has to be on my curve. And that means I'm going to come up like this, it looks like. And come down. And then as I move over here, it would be flat. Oh boy, here comes my left side. And then it would come back up like that. So if you think about your general solution, x squared over 2 plus x plus c, that plus c is just a vertical shift, isn't it? So we have all these vertical shifted parabolas that could happen. I could have one that came here, I could have one that came here, and so on. Okay? It gives you a visual representation to the solution of the differential equation. Questions on that? Okay. Okay, sometimes it's an integral that we have no idea. I mean, this one we know is going to be a parabola. Sometimes we don't. And sometimes we can only work with something like a flow field. There are equations out there that we can't integrate yet. But we could create a flow field to see what the solution would look like. Okay? All right, so let's move on. Now, solving differential equations. So this first one, our differential equation is dy dx equals secant squared x plus 2x plus 5. Find all functions of y that satisfy. All right, a few things to make note of. All functions y. Another way to say that is to find the general solution. And when they say general solution or all functions, they're looking for your answer plus b, because that accounts for all of the possibilities. Okay? So, before this section, we certainly would be able to find the function that we took the derivative of to get this. And what operation would we use to find that? We'd use an integral. So before this section, we would have just solved this by doing the integral of secant squared x plus 2x plus 5 dx. And we could still do this one this way, but I want to show a method that is going to lead us into more difficult problems where we have x's and y's mixed together. Okay, so we're going to develop this method now and apply it to harder problems as we go along. And the method is called solving differential equations by separation of variables. And basically what that means is we get our x's and dx's on one side, our y's and dy's on the other side. So if I have dy dx equals secant squared x plus 2x plus 5, and I want to get my x's and dx's on one side, y's and dy's on the other, what do? I multiply by dx. So I'm going to get dy equals secant squared x plus 2x plus 5 dx. And once we have, you're killing me, up here. Once we have separated the variables, then we can integrate each side. Okay, we'll integrate with respect to y over here, and we'll integrate with respect to x over here. So, what is the antiderivative of 1 dy? I heard it, y plus c. And then what do we get on the right side? What do we get? Tangent x, thank you for that. I need that a little louder. Tangent x plus x squared plus 5x. Now we have a c on the left and a c on the right, so I'm going to call this one c1.
Why isn't it x plus b?
Why isn't it what?
Wouldn't the integral of dx be?
We are integrating
Okay.
this whole thing with dx. Okay, over here, we are just integrating 1 dy. Whatever is being multiplied by the dy. So here it is 1, and here it is the entire expression. Okay?
The two c's aren't the same.
They are not necessarily the same. So, this is the only time you'll have to do it this way. From now on, I'll show you what you can do. But if we were solving for the general solution, we want to solve for y. So I would move this c over to the other side, and I'd be combining these two c's. Well, they're both constants, so I'm just going to name a new constant. I'm going to say let c2 equals c1 minus c. So now I can just write it as y equals tan x plus x squared plus 5x plus b2. Okay, so everybody listen, because I have to say this a few times before. Because I would always immediately move this c over and rename that constant, there's no real need to write the plus b on the left, because I'm just going to get rid of it. So, from now on, when separating variables, you will hear me say we'll manage our constants on the right side of the equation. So that means we just need the plus b on the right. You don't have to go through this plus b on the left, move it to the right, rename it, and so on. Okay, so from now on, you could jump right to here. Yes.
We still call it c2.
If you like to call it C2, you can. You can call it P if you want to. But I prefer C. You can just call it plus C or C, whatever number. Okay? Questions on this? Again, it looks like a little more work than what we have been doing, but it will be very helpful when we have more than one variable. Okay, So moving on. Now, we talked about a general solution. Here they ask us to find, and please make note of it, a particular solution. Listen up. A particular solution means that you solve for C. Means they've given you enough information so that you will solve for C. All right, so solving this one, what do we do? Move our dx over. Then, integrate both sides. Remember, this is 1 dy. The antiderivative of 1 is y. I don't have to write the plus b based on what we did on the last one. On the right side we have e to the x. Two x cubed? 2x cubed, yes. And then plus b. That is our general solution. And now we want to go on and use what is called the initial condition, or the value that they give us. Plug in 1 for x and 0 for y. And solve for c. So what is c equal to? What is it? You don't have to give me a decimal. So 2 minus e. Do we agree? Add the 2 over, subtract the e. Are we okay? So our constant is 2 minus e. So then our particular solution is y equals e to the x minus 2x cubed plus the quantity 2 minus e. What? All your life you just know. It was not postscript, it was particular solution. All right, are we okay on this one? Any questions? There's some writing going on, so I'll hold off a minute. Move on. Yep, that one we're not going to need to say. This one. So, using the fundamental theorem to solve an initial value problem. So, when they say initial value problem, generally that's solving a differential equation, and they give you a point to plug in. All right. So find the solution to the differential equation. Notice this time it's written as f prime of x equals e to the negative x squared. That is still a differential equation. And for which f of 7, I have to be very careful to make my lowercase f's here. F of 7 equals 3. What is the fundamental theorem of calculus? Landon, go ahead. The integral from... We'll say it. Well, let's do, that's part 1. I'm looking for part 2. We'll call it B in this case. I just want, how do we take B, how do we find a definite integral? It will be f prime in the one that we do here. I'm going to call it f for our original. Equals capital F of C. Good. Minus capital F of A, where capital F means the antiderivative. Okay. So in this problem, we want to use this process, but what we are trying, if we're trying to find the solution to the differential equation, f prime, our solution that we're looking for is lowercase f of x equals something. And they gave us f prime. So instead of doing the definite integral of f of x, let's do the definite integral of f prime. And I'm going to do it of t so that I can plug in my x when I need it. I'm looking for f of x, so I'm going to make my upper limit x. Any ideas of what to make the lower limit? Based on the information given. Not 3, but 7. And if we set it up like this, then what's the antiderivative of f prime? Lowercase f of x minus lowercase f of 7. Everybody okay with that? Just setting up our fundamental theorem with the information that they gave us. And then what we're trying to solve for is this. So lowercase f of x would equal what? Isolate this in this equation. We have the definite integral from 7 to x of f prime of t dt. And then what? Plus 3, which is the f of 7. So we get f of x equals the definite integral from 7 to x of f prime of t dt plus 3. And that is the solution we're looking for. We can now get rid of f prime. What was f prime equal to? E to the negative x squared. Oops, it'll be t in this case. And again, I only use t so that it's more clear when I'm plugging in my x, that we're not getting confused with variables. So there's our final. Your answer will have that definite integral in it. And just to let you know, this e to the negative t squared, to take that integral, looks like a very easy integral, but it is one that we have no method to help us get that antiderivative. So the only way we can find that integral is by using something we'll learn later, which is series, to get there. All right. See what I want next. This one just shows, the only reason I included this example from the book is the terminology. They say graph a family of functions. That again means the general solution. So you may see that terminology versus general solution. It's all the possible vertically shifted solutions to our differential equation, dy dx equals cosine x. Notice all of these are sine curves, correct? You see them all starting here, going up and down, so they're all sine functions, differing by just that vertical shift up and down. Nothing you need to write there. All right, let's take a look at this. Matching slope fields with differential equations. So, this happens quite a bit on tests, and I think your best approach is to think about where the slope will be 0 and where the slope will be undefined. Those are two easy things to find. And then look at the slope field to see if it fits that information. So number 1, dy dx equals x minus y. Well, x minus y is defined everywhere, so it's not undefined, but it equals 0. The slope will equal 0 when y equals x. Correct? Okay. So looking at these graphs, and I have my solutions already up there, so let's look at B. Does it make sense that that is, that the slope is 0 on the line y equals x? Well, let's take a point. So let's say our solution had to come through here. I'd come down like this, it levels out, and then it comes back up. Yes? We don't really see the horizontal line, but it's got to be there because I have a negative slope and then a positive slope, so it's got to level out. And where is that curve happening? Right along the line, y equals x. So this one matches number 1. Okay? Number 2, x, y is defined everywhere, but the slope will be 0 when x equals 0, and it will be 0 when y equals 0. Right? That's how we can get zeros for our slope. So then, if we look at b, x equals 0, horizontal tick marks right here. Y equals 0. Well, if we look at what's happening here, what's happening at the x-axis is the turnaround point. So at y equals 0, we still have a slope of 0. So that one fits. No. On these, if I had a point here and came up, I would be coming vertically up to this, right? Not horizontally. A slope of 0 has to be horizontal. Now, convention for slope fields. When we have undefined slopes happen with a vertical line, correct? So you can either put the vertical tick mark or you can leave it blank. But visually it makes more sense to put the vertical tick mark. So that's what's happening in here is we have vertical tick marks going on. Alright, number 3, x over y. So it's undefined when y equals 0, and it's 0 when x equals 0. And that one is the one that will match it. And then finally, y over x, it switches, and we are at p. So we're undefined at x equals 0. There are vertical tick marks there. And we are 0 at y equals 0. Someone asked in the last class what these functions would look like. Well, if I drew a solution to this one, and I'm not very good on this Moby board doing it, but I'll do my best. Again, we want to follow the slope. No, I don't know why I can't do that. I can't. But it goes something like that. Comes down and something like that. Okay? Now, for the AP exam, generally speaking, their general convention is that the solution to a slope field should be a function. So you would not run into one like letter A on the AP test. All right? Just take practice in dealing with these. If you were to find out this information, you were still unsure, then pick another point and go see if the slope matches what it comes out to be when you plug in x and y. Okay? All right. Now, last thing I want to get to is Euler's method. I need a table on your page. The last thing you know, stay awake. So we need a little table. Anytime you do Euler's method, there is a table involved. What's that? It should, yeah. Too narrow, wide. All right. First off, Euler's method is a way for us to determine or to approximate y values on a function using the tangent line. So we are going to use the differential that we've talked about in previous chapters to help us figure out what the next y value would be. So if you look over here, we have the point 2, 0 given to us, and then there's a little tangent line drawn there. And what we're going to do to approximate the y value at 2.2 is we're going to use that tangent line to find the y. And then we'll use another tangent line to find the next y, and so on, to help us move along the curve. All right, so to do this, I set my table up a little different than they do in the book. You can look at both and see what you like. We have an x and a y. Then we will find the differential in y, how far we have to move in the y. And then we will find a new y. And if dy dx is x plus y, then what is dy equal to? X plus y times dx. And notice that they gave us, and they will give us, our dx or delta x and they give us a starting point, f(2) equals 0, so that's our initial one here. We have 2, 0, and they want us to approximate f(3). So we use our delta x and we go up by that much until we get to 3. 2.2, 2.4, 2.6, 2.8, and 3. The only y value we know is the one that goes with 2. So we want to find dy, which you told me is x plus y times dx. And then we want to add it to our existing y to get our new y. So our new y is y plus dy. All right, so let's do our first one. X plus y would be what plus what? 2 plus 0 times, what's the x? 0.2. And we get? What's our dy equal to? 0.4. So to get our new y, we take our current y, 0, and we add our dy, 0.4. Then we write that one. That is our y value for 2.2. And then we go again. It's just an iterative process until we get down to the y value that goes with 3. So what do I plug in for our next one?
2 plus 2.2 plus 4.
Times 0.2. And we get, what is that? Point what?
4.
I don't think so. 0.52? Yep.
Oh,
Yes. And we take our current y, 0.4, and we add 0.52, and we get 0.92, and that's our next y. That's the y for 2.4. So please keep going, fill in your table, and we want to get our y value that goes with 3. So everybody's doing this. Just takes a couple minutes, and then we'll move on to, yeah, go ahead. Then we'll move on to reviewing homework. Calculators out, let's go. Yes, right. Good one. When you get to 3, let me know what our y value is, please. Anybody have a y value for 3? AJ?
3.4676.
Yep. 3.465. We'll go to 3 decimal places here. That'll do it. It was 3.46496, I believe. Any trouble getting to that? All right, this video will go up tonight, and I will fill in the rest of the table so we have it. One through 10, 13, what else? 19, 22, 25 through 28, 30, 32, 35 to 40, 55 through 58. Got it. Now it's on the video.